Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we'll be doing Unit 10, Lesson 6 on reflecting functions across the x-axis. All right, so far we have vertical and horizontal shifting, and we have vertical stretching and compressing. So let's now get into what we can do to reflect or flip a function across the x-axis. Here we go. Multiplying by a negative constant. We saw in the last lesson how multiplying a function by a positive constant would either stretch or compress the function in the vertical direction. In this lesson, we will look at the effect of multiplying by a negative constant. So let's take a look at exercise number 1. The function f of x is shown graphed. It is known that it has the form f of x equals the absolute value of x plus k for some value of k. What is the value of k? Justify your choice, then write the equation for f of x using k. All right, great. Well, we should understand what the parent function y equals the absolute value of x looks like, and we should be able to use that along with this graph to figure out what the value of k is and be able to write an equation for f of x. So pause the video now and see if you can do that, and feel free, of course, to use your graphing calculator to verify whether or not your choice is correct. All right, well, the absolute value of x, right, is this v that is right at the origin. This thing is the absolute value function that has been shifted down 4 units, and therefore k must be equal to -4, right? And we can justify that, because it's y equals absolute value of x shifted down 4 units. All right, therefore f of x is equal to the absolute value of x minus 4. All right, so we just wanted to really get the formula for our starting function. All right, let's take a look at letter B. The function g of x is defined by the equation g of x equals negative f of x. Give a formula for g of x, show how you found your formula. All right, well, let's just use the substitution property of equality like we always do, and I'm going to take absolute value of x minus 4, and I'm going to substitute it in here for f of x. Now, I want to be good about my use of parentheses, as always, so g of x is going to be negative absolute value of x minus 4. Now, we've seen stuff like this before, right? And the way that we want to interpret that really is as -1 times the absolute value of x minus 4, and now I'm going to distribute that through. Now, it would be tempting to put that -1 inside of the absolute value bars, but we cannot do that. We can't take a number outside of an absolute value bar and suddenly put it inside of the absolute value. The best that we can actually do is just keep that negative symbol outside of the absolute value, and then of course -1 times -1 times -4 is positive 4. So there is our formula for g of x. G of x is equal to the negative absolute value of x plus 4. Okay, letter C. Use your calculator to create a table of values given your formula for B. Show your table of values and graph g of x. All right, let's do it. Let's grab our graphing calculator. All right, let's open it up. I think the first thing I'm going to do is throw in that original formula. All right, so we've got our absolute value, right? And that was the absolute value of x. I need to use my right arrow, minus 4. So this is just our original function, right? There it is, great. All right, now our next function is negative, right? Then I go in, I grab my absolute value function, absolute value of x, use my right arrow to get out of there, plus 4, and there is our f2, or our, whoops, all I want to do is move that thing. Although that actually did pretty well. All right, there it is. Now, I need to create that table of values as always because I need to be able to put it up here on the graph. So I'm going to go into my menu, open up myself a table, split screen table. I don't want the original values. I'm going to go over to my second one. Now a calculator asks, do I really want f2? And I say yes. All right, so here is my table. I'm going to kind of go backwards a little bit, so that I can see some of these values. Maybe I'll start there at -4, 0, -3, 1, -2, 2, etc. Okay, so I've got my table of values. I've got to make this calculator small now so that I can get that table on my worksheet. Let's go full screen. All right, we'll put it over here, and then maybe we'll just get that table of values right in here. X and Y, I'll start at -4, 0, and then -3, 1, -2, 2, -1, 3, 0, 4. Gotta go down a little bit. 1, 3, 2, 2, maybe do one more, and 3, 1. All right, we will now plot this. Let's see if I can keep this on the screen. -4, 0 is right here, -3, 1, -2, 2, -1, 3, 0, 4, 1, 3, 2, 2, 3, 1. That's enough, I think. Plus I've got my graph anyway. We've got that, and there's our g of x. All right, which is exactly what we see on the graphing calculator if it was still open. All right. Here we have them a little bit better in color. Let's take a look at letter D. How would you describe the transformation that maps the graph of f of x to the graph of g of x, right? In other words, how do you produce this graph of g of x given that you have this graph of f of x? Well, this is the thrust of at least this portion of the lesson, which is that simply if I took f of x and I flipped it across the x-axis or reflected it across the x-axis, it would produce the graph of g of x. So if I reflect f of x across the x-axis, it will produce g of x. Now, think about why that is, right? For a moment, just consider this. All we're really doing when we do this is we are taking every y value on the function f of x and we're multiplying it by -1, right? We're not doing anything to the x's. We're just taking every y value on this blue graph and we're multiplying it by -1. So when I have this y value down here of -4 and I multiply it by -1, it becomes a y value of +4. When I take, let's say, a y value over here of, I don't know, let's say 4, and I multiply it, or 5, and I multiply it by -1, it comes down here to become a y value of -5. And that's exactly how we reflect points across the x-axis. We leave the x-coordinates completely alone, and we multiply the y-coordinates by -1. So, to summarize, reflecting a function across the x-axis, if f of x is any function, then g of x equals -f of x, or g of x equals -1 times f of x, these are exactly the same thing, we'll have a graph that is the reflection of the graph of f of x in the x-axis. All right, so let's take a look and see if we can use that fact. Exercise number 2. The function f of x equals x squared minus 4x is shown graphed. The function g of x is defined by g of x equals -f of x. Letter A, give a formula for g of x. Awesome. Well, why don't you go ahead and pause the video now, and using this definition for g of x and this definition for f of x, see if you can come up with a formula for g of x. All right, well, let's do it, right? G of x is going to be -f of x. And now if I distribute through a multiplication by -1, I'll find that g of x is -x squared plus 4x, right? Everything in the formula for g of x, or sorry, everything in the formula for f of x changes sign. Originally it was a positive x squared, it's now a -x squared. Originally it was a -4x, it's now a positive 4x. Now letter B, draw a graph of g of x. All right. Now, don't get me wrong, we could totally take this formula, plug it in our calculator, get a table of values, etc., except we want to be able to look at this definition and go, oh, okay, that means the graph of g of x is just going to be the graph of f of x after it's been flipped across the x-axis. So what I want to do is take every important point on this particular parabola and change its y value to be the opposite of what I see there. So for instance, this particular point that's up here at positive 5 will now be down here at negative 5. This point at 0 isn't going anywhere because the negative of 0 is 0. This point at negative 3 will now be up here at positive 3. This point at negative 4 will be up here at positive 4. Again, well, here at negative 3 will be positive 3. The 0 will stay where it's at. And that 5 will go down here at negative 5. And we get g of x, right? Real easy to flip a function across the x-axis. Just take all the nice points, all the convenient points, and simply change the sign on their y-coordinate and replot. Now, letter C, verify your equation in g of x is correct by using your calculator. Awesome. All right, so let's now take a look, right? We can open up our calculator. All right, we're not going to generate a table of values. In fact, I'm going to just go in and open up a new document. Come on. There we go, add a graph. And what I'm going to do is just like before, I'm going to put in f of x first. So I'm going to put in my x squared minus 4x first. Right, now I'll put in my second one, which was negative x squared plus 4x. And I won't even modify the windows, right? I'm just going to leave it like that because it's pretty easy to sort of compare these two right now, right? And it tells us, all right, yeah, we got it right? We distributed the multiplication by -1 correctly, and I definitely see this symmetry, right? We'll see the symmetry of the two functions across the x-axis. One of them looks exactly like the other one if it was reflected in the x-axis. Now, there's no way we can build an entire lesson just on multiplying a function by -1. So now let's talk about what happens when we combine reflections across the x-axis along with vertical stretches. And we can do that by simply multiplying by a negative number other than -1. Right, so when we multiply by -1, it just takes a number and it changes its sign, right? That's, by the way, a very important thing in mathematics, right? Multiplying any number by -1 leaves the size of the number the same, but it changes its sign, right? 5 times -1 is -5. -7 times -1 is +7. But if we come along and we multiply by a negative number other than -1, it will both change its sign and it will change its size. So let's take a look at that in exercise number 3. The parent quadratic function y equals x squared is shown graphed on the grid. Letter A, how will the graph of y equals 2x squared compared to the graph of y equals x squared? Use your answer to sketch a graph of it on the grid, label with its equation. All right, well, how will the graph of y equals 2x squared compared to the graph of y equals x squared? Pause the video now and see if you can answer this question. Well, it will be, this is from our last lesson, it will be stretched vertically by a factor of 2. You could say that, or you could say every y value will be twice as large as the y values on y equals x squared, right? That's the point, right? 2 times x squared versus 1 times x squared. So either way, like each y value will be twice as large. Or you could say it will be stretched by a factor of 2. Now, how do I use this then to create a graph? Well, it's awesome. I look at every point on here that it makes sense to look at. I take a given point, I look at what its y value is, I multiply that y value by 2, and I replot the point. Now, the one up here at -3, 9 would suddenly become -3, 18. Can't really plot that on this grid. But this one at -2, 4 can suddenly be stretched up to -2, 8. Right? So this thing is going to suddenly be up here at -2, 8. This one at -1, 1 will just go up to -1, 2. The one at 0, 0 will stay there because if I multiply 0 by 2, I still have 0. This one will have a y value now of 2. This one will have a y value of 8. and I can now graph that. That doesn't look great, but it is the best we're going to get. Y equals 2x squared. Excellent, right? And of course, what we see is we've seen this stretching, right? The parabola has gotten more narrow as we've stretched it vertically and as we've fixed, right, that 0. All right, let's take a look at letter B. How will the graph of y equals negative 2x squared compare to the graph of y equals positive 2x squared? Use your answer to sketch a graph of it on the grid. Label with its equation. Well, again, this graph, y equals negative 2x squared, will simply be this graph after it's been reflected across the x-axis, right? Because all I'm doing to go from here to here is multiplying the formula by negative 1. So it will just simply be a reflection across the the x-axis. All right, and that's cool, right? Because I can now take all of these points on this newly graphed function, right? I can take each one of those y values and simply negate it, right? Simply multiply it by negative 1. So this one that's now up here at positive 8 will now be down here at negative 8. This one at positive 2 will now be down at negative 2. The 0 will just stay there. Again, that will go down to negative 2, and this one at positive 8 will also go down at negative 8. So we have our parabola here, and that's y equals negative 2x squared. Now don't get me wrong, like we could literally go from the original y equals x squared and get this one by simply taking every y value on the original function, y equals x squared, and multiplying it by negative 2, right? Because this is y equals negative 2 times x squared, right? We just take all the original y values and multiply by negative 2. All right, so let's do one last one. Letter C. Graph the function y equals negative 1/2 times x squared on the grid by both reflecting and compressing the graph of y equals x squared. Now, one of the things that I've always found remarkable about these types of problems is I don't really even need to know about reflections or compressions or anything like that. This, compared to this, literally says I should take every y value on this and multiply it by negative 1/2. The y values on this curve are equal to x squared. The y values on my new curve are equal to negative 1/2 times x squared. So I could come here, right, and I could take that point at 9, and if I multiply it by negative 1/2, it's a little bit ugly because it would become negative 4.5, but I could do that, right? I divide by 2 and I multiply by negative 1. Here's a little bit of a nicer one. Right here, this y value of 4, when I multiply it by negative 1/2, will become a y value of negative 2. This y value of 1, when I multiply by negative 1/2, will become a y value of negative 1/2. This y value of 0 will stay at 0, then another negative 1/2, then another negative 2, and then a negative 4.5. And I get that function. And again, notice, right? That function has both been flipped across the x-axis and it's been smooshed. That's now a technical math term, smooshed, right? It's been compressed so that it's gotten sort of closer to the x-axis. And that's due to the 1/2. The fact that it's been flipped across the axis, that's due to the negative. All right, let's keep working on this. Take a look at another problem. Now, it's important to be able to identify the multiplying constant. So it's one thing to be able to like take a constant and produce another graph. It's another thing to be able to actually identify the constant from a given set of graphs. So let's take a look at exercise number 5. Two waveform functions are shown graphed below with g of x, that's the one in red, equal to k times f of x. F of x is the one in blue. What is the value of k? Show or explain how you found your answer. All right, well, what I'd like you to do is pause the video now and see if you can figure out what the value of k is and how you might go ahead explaining it. Take a moment on this. All right, well, the key is to come somewhere to a particular x value that's easy. Now, I like the x values that give us the turning points. For instance, right, let's take a look at this, right, and that's the point 0, 2, and take a look at this, and that, I'm sorry, that's not the point 0, 2, that's the point 2, 2, and then this particular one, which is the point 2, -6, okay? And remember, this one is the one that's coming from this one. You don't have to worry about the x's. The x's are staying the same, we're just transforming the y's. So literally, we could say to ourselves, well, -6 is equal to 2 times k, so k is equal to -6 divided by 2, and k is equal to -3, right? And that makes sense because we've taken that blue graph and we've flipped it across the x-axis and we've stretched it out, right? Every single y graph on the red curve is -3 times the y graph on the blue curve. Let's take a look at letter B. Given the function h of x equals 1/2 times g of x, plot a graph of h of x on the grid as well. Now, be careful here, right? H of x is 1/2 times g of x. H of x is not 1/2 times f of x. So pause the video now and see if you can graph h of x. All right, well, it's pretty simple, right? Here we're not going to have any reflections. H of x is simply going to have y values that are all 1/2 of the y values on g of x. So for instance, here, where we have a y value on g of x of 6, h of x will have a y value of 3. Right? Likewise, here, where h of x has a y value of -6, right? Oh, I'm sorry, where g of x has a y value of -6, h of x will have a y value of -3. And likewise, right, +3, -3, +3, and all of those zeros, remember, are not going to go anywhere under a vertical dilation, or sorry, under a vertical stretch, also known as a dilation. And there we go. And that graph right there is going to be h of x. Sorry about the overlapping colors there. You got blue and you have blue. But that's it, right? And again, whether we're talking about a positive value of k or a negative value of k, the big difference there is if it's negative, it's not only going to maybe change, the shape of the graph, but it's also going to reflect it across the x-axis. Now, the shape won't change if we multiply by -1, but its orientation will as it reflects across. All right, let's wrap this up. Now, what we saw today, really, at its essence, wasn't just reflecting across the x-axis. When we want to reflect a function across the x-axis or its graph, we multiply that function by -1, right? And that means every single one of those y values that were positive will suddenly become negative. Every y value that was negative would suddenly become positive. We can combine that with stretching and compressing by multiplying by a negative number other than -1. So if we multiply, let's say, by -5, we will both reflect and stretch. Or if we multiplied, let's say, by a number like -1/4, we would both reflect and compress, right? But at the end of the day, regardless of what you're doing, you're ultimately just multiplying the y values by a particular number. All right, we're going to see this just a little bit more in the last lesson of the unit, which is lesson 7. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.